Hi, my name is Michalis, and in this talk I'll talk to you about stateless model checking. Stateless model checking is a verification technique that verifies a concurrent program by enumerating all of its interleavings. And because enumerating all of the interleavings of a program doesn't scale, stateless model checking is usually combined with dynamic partial dereduction. Dynamic partial dereduction says that instead of enumerating all the interleavings of a program, we can simply enumerate a representative subset. And what does this mean? Well, if these are all the interleavings of a program, DPOR partitions these interleavings into equivalence classes and then tries to explore one interleaving per equivalence class. Dynamic partial dereduction is a very nice idea, but all existing DPOR approaches suffer from the following trade-off. They'll either explore an exponential number of redundant executions while maintaining polynomial memory consumption, or they'll explore zero redundant executions but then have exponential memory consumption. In this video, I'll talk to you about Trust, our truly stateless model checker that provides the best of both worlds: zero redundancy and polynomial memory consumption. Concretely, Trust is the first exploration optimal DPOR that has linear memory requirements. In addition, Trust is parametric both in the choice of the memory model and in the equivalence partitioning used by the DPOR. Trust is also embarrassingly parallelizable, meaning that separate explorations share absolutely no state and then they can be explored completely in parallel. And it is also verified in Coq. So let me give you a glimpse of how Trust works. In this program here, we have 4 threads. Each thread has one instruction, and these instructions can be interleaved in 24 ways, and these interleavings can be grouped into 4 equivalence classes. Trust models these equivalence classes by using execution graphs, like these here. In these graphs, the nodes correspond to instructions of the program, and then green edges show where the reads are reading from. So, in order to verify this program, instead of enumerating interleavings belonging in the corresponding equivalence classes, Trust verifies it simply by enumerating these 4 graphs here. And let's see how it does that. The procedure is actually pretty simple. We start from an empty graph, and then we add events corresponding to instructions of the program, starting from left to right. Whenever we encounter a read that can read from more than one places in the graph, then we explore both scenarios, either recursively or by using a stack. In this case here, this read can read both 1 and 0, and this is why Trust initiates 2 separate explorations. Now let's just focus on the exploration above for a second. In the next step, we'll add this right of x, and we'll get graph number 2. But when adding this right of x, Trust notices that if this right were added before this read of x, then this read of x could have read from it. So what Trust does is that it revisits this read of x, that is, it initiates a recursive exploration that models exactly this scenario. And actually, if we continue this exploration here, we'll get graphs 3 and 4. But instead of doing that, let's focus on this exploration here instead. In the next step, we'll add this right of x again. And now we make the same observation, that this read could have read from this right. However, we don't want to initiate another recursive exploration like this one, because then we'll get the same graph twice and our algorithm will not be optimal. So here's Trust's key idea. Trust will only do this revisit from this right to this read in the graph where the events in between the write and the read participating in the revisit were added in a maximal manner. And when is an event added in a maximal manner? Well, we say that the read has been added in a maximal manner when it's reading from the write that was added latest in the same memory location. For example, in this graph here, this read is reading 1, so the revisit will happen in this case and in this exploration. But in this exploration, this read is reading 0 and not 1, so the revisit will not happen in this case. We call graphs that satisfy this condition maximal extensions, and if you want to find out more about maximal extensions and why they guarantee polynomial memory consumption, please come to our full talk or read our paper.